Introduction: the Sun is the star at the center of our solar system, an enormous ball of hot gases that provides energy and light to our planet. It is by far the most important astronomical object for life on Earth. With a mass that makes up more than 99.8% of the total mass of the solar system, the Sun's influence extends far beyond its gravitational pull. It governs the behavior of all the planets, moons, comets, and asteroids that orbit it. Understanding the Sun is key to understanding not only our solar system but also the broader mechanisms of star formation, energy production, and the dynamics of celestial bodies. Basic characteristics of the Sun: the Sun is a star, which means it is a massive ball of hot, glowing gas that generates energy through nuclear fusion. It is primarily composed of hydrogen, about 75%, and helium, about 24%. With trace amounts of heavier elements such as oxygen, carbon, neon, and iron. Size: the Sun's diameter is about 1.39 million kilometers, about 864,000 miles. This is roughly 109 times the diameter of Earth, meaning over 1 million Earths could fit inside the Sun. Mass: the Sun's mass is approximately 1.989 times 10 to the 30 kilograms, or about 333,000 times the mass of Earth. This immense mass generates a gravitational pull that holds the entire solar system together. Temperature: the Sun's surface temperature is around 5,500 degrees Celsius, 9,932 degrees Fahrenheit, while its core temperature reaches around 15 million degrees Celsius, 27 million degrees Fahrenheit. The intense heat from the core is responsible for the energy it produces and radiates. Energy output: the Sun emits an enormous amount of energy, approximately 3.8 times 10 to the 26 watts, in the form of electromagnetic radiation. This energy is essential for sustaining life on Earth and driving the climate, weather, and ocean currents. The structure of the Sun: the Sun is divided into several distinct layers, each playing a crucial role in its behavior and the energy it produces. 1. Core: the core of the Sun is where nuclear fusion occurs. At temperatures of around 15 million degrees Celsius, hydrogen atoms are fused together to form helium. This process releases a tremendous amount of energy, which radiates outward from the core. The energy produced in the core is what powers the Sun and provides the sunlight and warmth that reach Earth. The core makes up about 20–25% of the Sun's total radius but contains nearly 50% of its mass. 2. Radiative zone: the radiative zone is the layer surrounding the core, extending from about 25% to 70% of the Sun's radius. In this region, energy from the core moves outward through the process of radiation. Photons produced in the core are absorbed and re-emitted by particles, a process that takes thousands of years to transfer energy to the outer layers. Despite this slow transfer, it is through the radiative zone that the Sun's energy begins its journey to the surface. 3. Convective zone: above the radiative zone lies the convective zone, which extends from about 70% to the surface of the Sun. In this layer, energy is transported by convection, the process of hot material rising, cooling, and then sinking back down. Hot gases from the interior rise toward the surface, cool as they approach the outer layers, and then sink back down to be reheated. This constant cycle creates convection cells, which are visible on the Sun's surface as granules. 4. Photosphere: the photosphere is the visible surface of the Sun, where the light and heat that we see and feel originate. While it is often referred to as the surface, it is actually a layer of gas about 500 kilometers thick. The temperature of the photosphere is around 5,500 degrees Celsius. It is in this region that the Sun's light, or electromagnetic radiation, is emitted into space. Sunspots, which are cooler and darker regions on the photosphere, occur due to magnetic activity and are often associated with solar flares. 5. Chromosphere: above the photosphere is the chromosphere, a layer of the Sun's atmosphere that is about 2,000 kilometers thick. This region is best seen during a solar eclipse, as it glows with a reddish hue. The temperature in the chromosphere increases from about 6,000 degrees Celsius at the bottom to around 20,000 degrees Celsius at the top. The chromosphere is the site of solar phenomena such as solar flares and prominences. 6. Corona. The corona is the outermost layer of the Sun's atmosphere, extending millions of kilometers into space. Despite being much farther from the Sun's core, the temperature in the corona is much higher than in the photosphere, reaching around 13 million degrees Celsius. The corona appears as a halo of white light during a total solar eclipse. The origin of the corona's high temperature is still not fully understood, but it is believed to be caused by waves of energy and magnetic interactions in the Sun's atmosphere. Solar phenomena. Sunspots. Sunspots are temporary, dark, and cooler spots on the Sun's photosphere. They are associated with intense magnetic activity that inhibits the flow of heat from the Sun's interior. Sunspots follow an 11-year cycle of activity, with the number of sunspots peaking at the height of the solar cycle. These spots can influence solar radiation and space weather events. Solar flares. Solar flares are sudden and intense bursts of energy that occur when magnetic fields on the Sun's surface suddenly realign. These flares release a massive amount of radiation across the entire electromagnetic spectrum. Solar flares can disrupt satellite communications, GPS signals, and power grids on Earth. Coronal mass ejections, CMEs. A coronal mass ejection, CME, is a massive burst of solar wind and magnetic fields rising from the Sun's corona. These ejections carry millions of tons of plasma and can travel through space at high speeds. When directed toward Earth, CMEs can interact with the Earth's magnetic field, causing geomagnetic storms and auroras. Solar wind. The Sun continuously emits a stream of charged particles known as the solar wind. These particles consist mainly of electrons and protons. The solar wind affects the entire solar system, shaping the planetary atmospheres and interacting with the magnetospheres of planets like Earth. The solar wind also plays a key role in the formation of the heliosphere, a bubble-like region of space influenced by the Sun's activity. The Sun's influence on the solar system. The Sun's gravitational pull is the primary force that keeps the planets, comets, and asteroids in orbit around it. The orbits of the planets are governed by the Sun's mass and the laws of gravity. Without the Sun, there would be no stable planetary system, and life on Earth would not exist. Earth and the Sun. Earth is located about 93 million miles, 150 million kilometers, from the Sun, a distance known as 1 astronomical unit, (O). This distance is crucial for maintaining the conditions that support life. If Earth were much closer to the Sun, the planet would be too hot for liquid water to exist, and if it were farther away, it would be too cold. The outer planets. The outer planets, like Jupiter and Saturn, orbit much farther from the Sun, receiving less sunlight and heat. This affects their atmospheres and weather patterns. Jupiter's strong magnetic field, for example, is influenced by the Sun's radiation and solar wind. The Sun's life cycle. The Sun is currently in the middle of its life cycle. It is about 4.6 billion years old and is expected to remain in its current state for another 5 billion years before undergoing a series of transformations. Main sequence. The Sun is currently in the main sequence phase of its life cycle, during which it fuses hydrogen into helium in its core. This phase is the longest in a star's life and has lasted for about 4.6 billion years. Red giant. As the Sun exhausts its hydrogen fuel, it will begin to fuse helium and heavier elements, causing it to expand into a red giant. During this phase, it will shed its outer layers, creating a planetary nebula. White dwarf. After shedding its outer layers, the Sun will become a white dwarf, a dense, Earth-sized remnant of its former self. It will slowly cool over billions of years, gradually fading into darkness. Conclusion. The Sun is far more than just a source of light and warmth for Earth. It is a dynamic and complex star that plays a pivotal role in the structure and evolution of the solar system. From its enormous size and energy output to its fascinating phenomena like solar flares and sunspots, the Sun continues to be a subject of intense scientific study. As the heart of our solar system, the Sun's impact is felt on every planet and in every corner of our understanding of astrophysics. It is not just our source of energy, it is also a window into the nature of stars.